Okay, so today we are talking about electrophilic aromatic substitution reactions. More specifically within that, we are going to be considering why are electron withdrawing groups deactivating. And when we talk about deactivating, we are referring to the benzene ring and electrophilic aromatic substitution reactions, which essentially means the benzene ring needs to act as a nucleophile in this reaction, right? An electrophile is going to come along and the benzene ring needs to attack that, right? But it's not going to be able to do that if it is losing electron density, and that is what is happening with our electron withdrawing groups. So here we've chosen to put a nitro group onto the benzene. This is not the only electron withdrawing group. You could use an aldehyde, but this is a strong deactivator, and so I thought it would be a good example. So how I think about it is in terms of resonance, right? So we can see that this nitrogen has a positive charge, and we can see that this oxygen has a negative charge. But we know that this is not the true picture. While they are going to have partial charges, we know that charge, in this case, where we have resonance, is not localized. It is distributed, right? And so if we are going to draw out the resonance structure, and just bear with me because this is going to hopefully explain to you why they are meta-directors is sort of what we are actually looking at. Why are they meta-directors? So we see this pi bond is going to move up here, and that is going to stabilize that positive charge on the nitrogen, but that's going to create too many bonds. So we are going to move one of the oxygen bonds over onto the oxygen. So we're breaking that pi bond, and it's going to give us a negative charge. So we've still got that positive charge on the nitrogen, but it has pulled electron density out of the benzene ring, right? Now we've got a positive charge here, right? And so I mentioned this in my last video, but it's worth reiterating. When we talk about ortho, meta, and para, it is in reference to a substituent, right? So ortho, meta, and para are not a specific spot on the molecule regardless of anything. They are relative to something. So we've got a nitro group here. Relative to this nitro group, these two spots right here, bing, bing, are ortho positions, right? These two spots are meta positions relative to the nitro group, and that's the para position. If you have a different substituent, now ignore this for the rest of the example, but if you have a different substituent, these are the ortho groups relative to that substituent. These are the meta spots relative to the methyl substituent. And this is the para spot relative to the methyl substituent. So all I want you to know is that it's relative to something. It's not an absolute spot, is sort of what I'm getting at. And so when we draw this out and we watch the pi bond get broken and the electron density pulled out of that benzene ring, it creates a positive charge at the ortho position of the nitro group. Now, we know that if we want an electrophilic aromatic substitution reaction, our benzene ring has to act as an electrophile. So if this position has a positive charge, it's not going to be able to do that. It has been deactivated. And so, of course, there's more to it. There's another movement. And bear with me for a second. What's going to happen? This pi bond is going to break, move over here, and we're no longer going to have a positive charge there. Give me a second to just draw out the nitro group on top. Of course, I didn't draw the minuses on the oxygens to begin with, which I should have done. That was a mistake. Positive. And so, double bonds here. Now, our positive charge is here. This is the para position. And now we're seeing, oh, okay, so this is what's going on. That's why it's a meta-director. We've got a positive charge on the ortho in one resonance structure and a para in another. So we understand that. And just to show you the other ortho position, apologies, I'm not a very fast writer. Probably should get better at that, but oh well. I'm just going to use a different color to draw out our pushing of electrons for this resonance structure. Instead, we would have, of course, one thing to understand is that this is not an actual representation of what's going on. This is a more accurate representation because the electrons are delocalized. But so we can do something like this. Pretend the red lines aren't there. It's just the green lines at this point. We have this move up here, and using that, our resonance structure is a positive charge here. And so we can see, depending on where you move the electrons, you're going to get 3 resonance structures, one in which we've got a positive charge on one of the orthos, the other ortho, and then a para, right? So we can see that the only spot on the benzene ring that doesn't get the positive charge is, the group with a substituent already attached in the meta positions. So these reactions, if you compare it to a strong activator, these reactions with a strong deactivator are going to be immensely slower. A strong activator is placing partial negative charges on carbons, right? Obviously they're delocalized, but when we look at the resonance structures, that's what we see, a negative charge on it. So these are immensely slower, and in many cases the reaction just does not happen. And if it does happen, it's going to be on the meta spots because they're the only ones without a positive charge on them. I hope this has been helpful and that I haven't missed anything. Just looking to make sure. I don't think so. So yeah, I hope it's been helpful. Just trying to help out a little bit. If you have any questions, you can comment them below. Who knows if I'll be able to answer them though. I'm only a beginner. Thanks for watching.